Welcome to this project demonstration of an AI-based CCTV threat detection system. This system takes a live video feed from a camera, runs it through YOLO object detection models, and looks for people, bags, vehicles, and weapons. It tracks these objects over time, detects unattended bags, and sends SMS alerts when a high-risk situation appears. At the top of the code, the main libraries are imported. Ultralytics YOLO for object detection, OpenCV for handling video frames, Supervision for tracking object IDs, PyTorch for GPU or CPU selection, NumPy for calculations, and Twilio for sending SMS alerts. Next, some configuration is defined. There is a general YOLO model for detecting objects like persons, backpacks, handbags, suitcases, cars, trucks, buses, and motorcycles. A second YOLO model is loaded specifically for weapon detection, with classes such as knife, pistol, rifle, and grenade. Confidence and IOU thresholds control how strict the detections are. The video source is set to the default camera, and the code automatically chooses GPU if available, otherwise CPU. The Twilio section holds the account SID, auth token, the sender number, and the destination number. A cooldown time is configured so that SMS alerts are not sent too frequently. A fixed latitude and longitude represent the CCTV location, and a Google Maps link is created from this, so each SMS contains both the alert and the camera's position. Risk levels are then defined. Each type of object has a base risk. People are low risk by default. Bags and vehicles are medium. Colors are set for low, medium, and high risk so that bounding boxes can be drawn in green, yellow, or red. Behavior thresholds say how long a bag must stay without its owner to be considered unattended, and how much it must move to be treated as picked up or moved. The script then loads 4 models: the main object detection YOLO model, the weapon detection model, a ByteTrack tracker to keep consistent IDs for each object across frames, and a segmentation model used to check whether an object, like a bag, is actually on the ground. The camera is opened using OpenCV. If the camera cannot be accessed, the script prints an error and exits. A full-screen window is created where the annotated video will be displayed. To keep track of bags, a dictionary called bag states is used. For each bag, it stores when it was first seen, its last position, who the nearest person owner is, and whether that bag is currently considered unattended. Several helper functions support this logic. A distance function calculates how far 2 points are from each other. A risk aggregation function upgrades an object's risk to high whenever a weapon is detected or a bag is unattended. Another function uses the segmentation model to check if a detected object appears on the ground, which helps confirm that a bag is truly left there. The SMS function builds a short alert message, appends the Google Maps link, respects the cooldown, and uses Twilio to send the SMS. The core behavior runs inside the main while loop. For each frame from the camera, the image is resized and passed into the main YOLO model. Detections are converted into a format that the tracker understands, then filtered so that only the allowed classes, persons, bags, vehicles remain. The tracker assigns an ID to every object, so the same bag or person can be recognized across different frames. From these detections, the script builds 2 dictionaries, one for persons and one for bags, each storing the center point of the bounding box. For every bag, the nearest person is treated as its owner. If a new bag appears, its first seen time, owner, and last position are stored. If a known bag moves more than a distance threshold, its timer is reset and it is not considered unattended. If the owner disappears from the frame and the bag stays in the same place longer than the configured time, that bag's state switches to unattended. For each detection, the script then calculates the final risk. If the object is a person, a crop of that person is passed to the weapon detection model. If any weapon class is detected, the flag for weapon detected is set. If the object has an unattended bag state, the segmentation model is used to confirm it is actually on the ground. These signals are combined with the base risk. Any weapon or unattended bag results in a high-risk label. Whenever a high-risk situation is detected, an alert string is created, which includes the object type, any weapon name, and the time. The SMS function is then called, which sends a text message with the alert and the CCTV's maps link. Finally, the script draws bounding boxes around every detected object with a color that matches its risk level, and labels them with their ID, class name, and risk. The current frames per second value is shown in a corner, and the annotated frame is displayed. Pressing the Q key stops the loop, releases the camera, and closes all windows. In summary, the system takes a live CCTV feed, detects and tracks people, bags, and vehicles, checks for weapons on people, detects unattended bags using time, distance, and segmentation, assigns a risk level to each object, visually highlights them on the video, and sends SMS alerts with the camera's location whenever a high-risk threat is found.